perspective of an inverse. So if I have a linear equation and you're asked to solve for x, okay, how do you solve that equation for x? Yeah, you add 3, right? Why do you add 3?
More x by itself.
Okay. What's the relationship of these two items? They're inverses. Okay. Same with multiplication, right? How do you solve for x? We divide because multiplication and division are inverses. Okay. So, and then you can even extend it to something like that. Why? Because the roots and exponents or powers are inverses, correct? Okay, so the question would be, how would I solve an equation like that? See the roots have a numeric exponent. This is a numeric exponent. No, we cannot use a root to undo that. Okay. No, you're trying to solve for the value of x. So 10 to what power is 100? 2. So logically deduced, right? X is 2 because 10 squared is 100. Okay. Now, what if I gave you something screwy like this? It's close to cubed, because 5 cubed is 125, right? But are you going to guess the right answer? No. Probably not. Okay. We need something called a logarithm. Okay, so a logarithm and an exponential. They're inverses. And so this is how we will manipulate these two different situations. So we will solve exponentials with logs. Okay. So given this, let's look at their relationship, and then we will kind of flesh out how we use them. And I'll give you a couple examples and then we'll go. Yeah. So if I have something like that. This is an exponential, we have a base, correct? Okay. The base always stays the same. Okay, so a log base would be log base 5. We have our base here. What you do is you switch the exponent and the number. Okay, so now we need to put 134 here and x. And you can see how that x equals now, right? Yes. Okay, now the question is, what would that value be, right? That's a calculator problem. Okay. Anybody know how to do that with a calculator? No, we don't. Okay. Let's look at one that's a little more typical, and then we'll get to the calculator. So back to this one. Rewrite that as a log.
Log of 10.
Okay.
Log of 10, 100.
Yeah. So the question here is, what exponent of 10 makes 100.
Does that still come out as 2? Yeah.
Yeah, it's 2. Okay, you can rewrite it if you want like this. But it's very basic. Right, see how the log base 10 and the exponent, these will actually cancel, so 2 would equal x. So we can't actually do that here because this is not a perfect cubic. Right? Okay, so that's rewriting, that's the relationship, the inverse relationship between logs and exponentials. Okay. So on your calculator, okay.
Never mind.
Keep a couple things in mind. Common log, what we call a common logarithm, is base 10. So is this a common log?
Yes.
This is a common log, right? We would not write the base on it. This is typically how that problem will be written. So that would imply base 10. Anything else is going to be written with the base. Okay. So if you look at your calculator, that button, log, does it have a base?
Yeah.
No. It's base 10. Okay, so log 100 is that problem right there. Okay. What?
Who says we're going to change the base 10 to base 2? Is that the same thing?
Yeah.
Basically.
Basically. Okay, so if you want base 5, there are a couple ways to do it. Number one is just use your calculator. There it is. Log base. So go to the math menu, to A, log base, and it will give you a log where you can change the base. 5,134. 3.043, right? So you have to know this in order to solve that question properly.
Wait, so the base is 134
What?
When you input it into the calculator, the base was 134?
No, 5.
Oh, okay, I can see it.
How do you put in the base?
Huh?
How do you put in the base? And then just roll down.
So math, go down to, I think it's A, log base, hit enter, and then you type it in the appropriate boxes. Okay.
Put it in, I mean, at least.
This one? How?
The dot places of 1, that's 5 to 0, 5.
That's not right.
5
to
0 is 1.
Okay.
Yeah.
No, if you want to change that to base 10, it's called the change of base formula. This is not official yet, but that's the change of base. That's the other way in your calculator to do that problem. We just changed it to base 10, so you would go in and type log 134, whoops, clear that, divided by log 5. Okay, so there are two ways to do base changes. Put your parentheses in the right spot. Okay. All right. Good with that? It's just a transferring knowledge one way or the other. Okay. Let's look at the graphs. So if I graph y equals 2 to the x, point is 0, 1. Good. I'll do that. Okay, so remembering that inverses are just an x and y switch, what is the graph of log y equals log base 2 going to look like? What's this point going to become? 1, 0. Okay. We also could say, well, this is 1, 2. So what's another one?
2, 1.
2, 1. We could go to 2, 4, right? So this would be 4, 2. Okay, does this is a horizontal asymptote, so this one is going to have a vertical. So our graph is going to look like this. So again, all logs are going to look very similar to that. And it is always good to keep in mind that the log at 0 is 1. Oh, sorry, that's backwards. Log at 1 is 0. So, again, playing that inverse relationship with the graphs. Questions so far? Okay, let's work through a few problems here and see. Let's go with. Okay, rewrite as an exponential. Ready to go. Remember, put the base in the proper spot and switch the numbers. So rewrite that as an exponential just like we did here. What? I know what it is. You're going to find out next week. All goes according to plan. No, this is not a calculator problem. This is to rewrite it as an exponential. You take away the log and write it as an exponential like this. Base. And then switch the numbers. That's rewriting as an exponential.
So just put it to a log from an exponential, you just put log in front of it and switch those.
Right, basically. Try this. Rewrite that as an exponential. Whispers. Is that true? Yeah, it is. Again, illustrating that inverse relationship. And then again, we can write these as a log.
Exponential 3 equals 4.
What'd you say, Ken?
Log 64, exponential 3 equals 4. Doesn't make sense though.
Exponential 64.
Log base.
Oh.
I switched the numbers. Because this is 4 cubed, right? So again, you can rewrite this 4 to the third. And 64 is 4 cubed. Those cancel out, 3 equals 3. And on your way to solving log equations. Questions? How about we evaluate? This is no calculator. Okay. Again, what exponent of 7 is this?
7
Times 7.
7 squared.
It's not squared. It's 1 over 49. So we learned about some properties of
Oh, so
exponents.
two over
So
one.
what do you do with the exponents on the bottom?
Oh, 1 over 2.
So it's 49 is 7 squared, but it's 1 over 7 squared. So what do you do with the exponents on the bottom? Move it to the top and make it a negative. Remember that property? 7 to the negative 2 is the same as 1 over 7 squared. So what is the answer to that? What happens to log base 7 and the 7?
You cancel out.
So what's the answer?
-2.
So what exponent of 7? That's what you're asking. Because that's the base. Let's see here. Try this one. Go ahead. Okay, what exponent of 5? What's the question? This is 1 over 5 to the 4th, correct? And then that makes it 5 to the negative 4, so the answer is so those are no calculator logs that you can evaluate. Anything with a clean exponent, really, right? Any perfect square in here, or perfect cubic, or perfect fourth.
Do you think we'll know?
Not without a calculator. No. When I was in school, we barely came out with these calculators, but we had tables in our books that would have like 5 to the 3.01 and 5.03.02, and we have to go through and you can use logs and go back. It's kind of a mess.
Is that right?
Dated myself. That was 20 years ago. What?
Is that like the same as in stats where you have to use like the
sheets that have like the different numbers.
Exactly what it is. Yeah. All right, here's an example. We talked a little bit about the science applications and half-life, right? So, if you're looking at half-life of different radioactive materials, so there's, this is all in your book, but like arsenic 74 has a 17.5 day half-life. So every 17.5 days, half of it's going to be gone. And then half and half. Carbon 14, anybody know that one? I think I said it was in 6,000 ranges. Okay, so because this number is so large, carbon 14 dating, do we really know if it works over time? That's a question in my mind.
Wait, what?
Have we been measuring carbon 14 for 6,000 years? No, we haven't. So that's a scientific, educated work, guess, hypothesis that's been tested as much as possible, but we have not been around to actually see that in action for 6,000 years. Okay. There are problems with carbon 14 dating. Water affects it. Okay, so, and then you can get to stuff like, but plutonium, we can actually measure plutonium half-life because it's a half a second. So unstable, translation, it goes boom. It's a nuclear, that's one of the things that we use in nuclear weapons, plutonium. Okay. So more unstable can be used for nefarious purposes, we say. Okay. So let's see what we got. And then there's others. Here's one that we can do an example on. Thorium-234. 25 days. Again, you can actually measure that. Okay. So let's say we have 256,000 grams of thorium-234. How long will it take to decay? To get to 1,000 grams.
Oh, that would be.
So,
What did you call it?
okay, remember your exponential?
Yeah.
For science, this is typically the one we will use. Okay. This is exponential growth and decay model. Okay, so n is the final amount. What's that number going to be here?
1,000.
Okay. And sub-zero, yeah, it's the initial amount. We don't know the time. We know the rate. It's half-life, right?
Yes.
Okay, so half. So 1 minus a half is a half, right? Okay, so there's your equation to find out how much time in half-lives it's going to take.
Can we put 25 in there?
Yeah, we're going to have to use logs to solve this. 25 does not come into play yet,
So we do,
because this is number of half-lives. Then we will multiply that by 25 to get how many days.
no, we first have to.
Divide first. Okay. Just like a radical, you have to isolate the. Okay, so you have to
Should be 1
isolate.
over 256, right?
156, 1/2 to the 2. This is where
Oh, this is good.
logs come into play. What?
be base,
Base
log
one half.
base, one half, log base.
You all right? Don't hurt yourself. Log base 1/2, 1/256 equals t. Put it in your calculator. Oh my gosh, I've been tired. Eight half-lives. How many days is that? Howdy. Yeah.
Quick question for you.
Yeah.
Levi Martin, you cut a piece of wood here, so you want me to check if you're okay with me taking it ready to go.
Scrap bins. Yeah.
Sweet, thank you.
Let's do it.
There you go, 200 days. Again, that's something we can actually measure, so we know it's scientifically accurate. 25 days.
Yeah, what would happen? How is it? So it's 1,000. Yeah. So you know that we
Any questions? Yes?
What is this after log 1/2?
1/256. So we've rewritten this as an exponential, or as a log. Rewrite that log as exponential as a log. Calculator. There it is. Okay. No questions otherwise? Okay, again, we could get an earthquake, some pH and all that stuff in the logs. What is the magnitude of an earthquake? Let's say an earthquake pops off and it has 10 to the 7th joules of energy. What's the magnitude?
What are you getting?
On the Richter scale, right? The Richter scale. Any guesses?
No clue.
It's right there.
How's that?
7. Yeah, so all we do is use logs to simplify that to an actual usable public number. Okay. pH, same thing. If you have a pH of 7, the concentration of hydrogen ions in the solution is 10 to the 7th. There's 10 to the 7th hydrogen ions, so the pH is 7. We use logs to simplify these things. Okay. So again, you see that log inverse relationship with exponentials. So it does come into play a lot in science. So okay. I think that's what it is. I posted on Classroom today, but yep. Okay. So this due Tuesday, as long as I'm here. Just so you're aware, we don't know what procedures additionally they're going to happen here. I'm going to have to have surgery again. I will have to have the pin removed. I have to have a skin graft. So when I go to the doctor, I won't be here tomorrow. They might say, okay, you have surgery Tuesday. Yes, sir. Okay, so things are a little fluid, but I'll make sure that you always have some work to do. Okay. Tomorrow, you have an exponentials packet that you're going to work on. Okay. So it's kind of a real world. Anybody want to be a wildlife biologist? Considering it? Okay. Invasive species come in. They have no natural predators. They spread exponentially. That's kind of what you're going to be working on, is figuring out how fast those things can spread. Tamarisk is an invasive species.
And then calculate.
Okay, lots of other things, so, that's tomorrow, but that's you can do. Take advantage of your 10, 15 minutes, please.